Chemistry, how are we doing today? Hopefully y'all are all doing well. Today what we're going to be doing is going over the kinetic molecular theory of gases. So we're going to be starting day one, part one of our gas law notes on this unit. So for this, you do need to make sure you've got your notes, and then you also need to make sure you've got something to write with so that you can take your note. Now, for gases, one thing that we do kind of need to keep in mind is what we call the kinetic molecular theory. And basically what it does is it explains to us what's actually going on with the gas, and it allows us to kind of predict the behaviors that a gas would have. Now for this, something to keep in mind is that the kinetic molecular theory specifically applies to what we call an ideal gas. It's a gas that's doing exactly what it should be doing. Now we do recognize that in the real world, things don't do exactly what they should be doing all the time, but we try to kind of come up with this situation where it's like in the ideal, in the perfect world, this is what they should be doing, right? Okay, so for the kinetic molecular theory, there's 4 rules that you need to know. The first one says that particles are so small compared to their distance between them that the volume of an individual particle is assumed to be negligible or zero. So essentially what it's saying is that if I'm talking about an individual gas particle, then I'm going to assume that it has no volume. Okay, if it's just a single one, only one gas particle, I'm going to assume that it has no volume. Now we know that gases actually do have volume, right? And a lot of times when we talk about gases, we don't talk about just a single particle. We'll talk about an area of volume of those gases, right? And so that's just something to keep in mind. If I'm focused on a single particle, then we assume that its volume is 0. Okay, because it's so tiny. Number 2 says particles are in constant motion. The collisions of the particles with the walls of the container cause it to exert pressure. So a lot of times a common misconception is that pressure is just something that happens. Pressure is actually the gases that are in that container colliding consistently with that container. So like atmospheric pressure, the reason that we have pressure on our bodies is because the gases that are in the air are actually pushing down on you. Okay, and so that's just kind of something to keep in mind. Now we know that gases are in constant motion. We know that all matter is in motion to some extent. Just gases are more freely moving around, right? Because they can actually expand to fill whatever container they're in. Okay. Rule number 3 says the particles are assumed to exert no force on each other. They're assumed to neither attract nor repel each other. Okay, so what does that mean? What does that actually look like? Well, essentially what it means is that when a gas molecule or particle collides with another gas particle, what we'll see is that in the perfect world, no forces are exerted, which means they're going to maintain the amount of energy that they had. And so we know that that's obviously not perfectly the case. We know that if something's got more energy, it's going to transfer some of that energy to the other particles. But in an ideal situation where we've got a constant temperature and pressure, then we could see some of that ideal behavior actually happening. Okay. Now we also assume that they do not attract nor repel one another. And so basically that's just saying, okay, well, because these gases are neutrally charged, there's not going to be any attraction or repulsion. Okay. The last one is the average kinetic energy of the collection of gas particles is assumed to be directly proportional to the Kelvin temperature. Okay, well, why does that make sense? Well, it makes sense because temperature is average kinetic energy. So when we talk about temperature, we're saying the average of all the molecules in this area are going to have this temperature. So why don't we actually look at each individual molecule if we're talking about, or particle, if we're talking about temperature? Well, we don't look at each individual one because it doesn't make sense to. Everything is going to have a different kinetic energy. You'll have some that are moving faster, some that are moving slower, and so we do just need to take that into account. And so a lot of times it doesn't make sense for us to measure a single particle. So we look at the average of all the particles in that area. All right. And we assume it's directly proportional to the Kelvin temperature because, well, again, Kelvin is just a measurement of temperature, right? And so it's just saying that if we're talking about the average kinetic energy, it should be proportional to the Kelvin temperature. So the temperature, the average kinetic energy in Kelvin. Okay. All right. Now, again, we do recognize that real gases do not conform to these assumptions. Real gases kind of do their own thing. And so we do need to keep that in mind when we're talking about these. But a lot of times we just make the assumption, unless we're told otherwise, we make the assumption that they're ideal gases. All right, y'all. So that is the end of your notes on the kinetic molecular theory. Please don't hesitate to reach out if y'all have got any questions. But otherwise, y'all have a great rest of the day. Bye, y'all.